So let's start the third lecture today. The fifth lecture. Okay. So yesterday we proved Lamperti's representation theorem. In, or let's say, 4 positive processes. Okay, so we gave the proof of that, essentially complete. There was something that I didn't check, that I will check today, okay? And also there was an identification of the Lévy process associated to a stable process killed at -∞0. Okay, so we check that the stable process killed when it goes below 0 is self-similar. Okay, just the killing doesn't change the scaling property. Okay, and we identified the Lévy process that is associated to it. Okay, and then we also built or identified the Lévy process associated to a stable process condition to stay positive and or to hit 0 continuously. Okay. Well, this was slightly fast at the end, so I will recall a couple of facts now. But let me check first the 2 gaps that I left here. One of them was to prove that the definition of psi in Lamperti construction does not depend on the starting point. So psi t defined as log x bt over x0 for t positive does not depend on the starting point. Okay, so I did that claim. Okay. So to check that, I said we needed to introduce, as yesterday, the process x tilde t, which is c times xt c to the minus alpha starting from x. Okay, so just take c positive and this process like that. Okay, this process is a positive self-similar Markov process that starts from c times x. Okay, so it starts at c times x. Okay, so how does the time change look for this process? So let's call b c times xt the inverse of the functional that is used here. So s positive such that the integral between 0 and s of x u c minus alpha c to the minus alpha x du is bigger than t. Okay? So now, make a change of variables here. B equal to U times C to the minus alpha. Okay? So dV is equal to C to the minus alpha du. Okay? So we will get that BTCX is equal to the first S, such that the integral from 0 to S times C to the alpha x u to the minus alpha du is bigger than t. Yeah? U is between C minus alpha. Okay? And just make a change of variables, and you will see that this is C alpha B T, but starting from x. Okay? That is one point. Okay? And then plug this time change into this process. So take, call it, let's see psi t to be the log of that process. So C x x t C to the minus alpha in B C x t divided by x x 0 C to the minus alpha C. Okay? So just apply the definition of psi, okay, to that process that I have here. Okay? But by this construction, okay, we have that this C and this C cancel, and the C that is here, okay, C times x, let's call it, okay, it's B x t over x0 of x. Okay? But this is just psi t starting from x. Okay? And this holds for all t. Yeah? Okay, so I'm taking a self-similar Markov process that is starting from C times x. Okay, this is just a representation of that process. Okay, I see how B depends on C by getting this. Okay, and then I plug the process I that depends on the starting point. Let's make obvious the dependence on the starting point. So let's say it depends on the starting point and it's C times x. Okay? So we just plug each of the quantities, okay? And we get that this guy here is equal to this one, okay? But this guy has the same law as the process starting at C times x, okay? So with these two identities, what I get is that there is no dependence on x, because this holds for every C positive, okay? So there is no dependence on the starting point, okay? Is that okay? Yeah? Somebody checked that before, maybe? Somebody did the homework? Guys around there? No? Okay. Here? You did it? You didn't? Okay. Well, that was the first thing to check, okay? And this is the key fact for Lamperti transformation, okay? That was one of the gaps I left yesterday. Okay. What about the other one? The other one was verify the identity. So if we have psi s, I will Yeah, I will use the notation psi for Lévy processes in this bit. Okay, so psi, a Lévy process. Okay, and with Lévy measure. Pi, okay, and take tau 0 minus the first time that psi goes below 0. Okay? And let's determine the expected value starting from little x for psi of tau 0 minus in the event, okay, where psi at tau 0 minus is smaller than 0. Okay? So this event, psi tau 0 minus strictly smaller than 0, is when psi passes below 0 by a jump. Okay? And I want to verify this is equal to the expected value starting from x, the integral between 0 and infinity, of pi of minus infinity minus psi t when t is smaller than tau 0 minus ft dt, okay, for every f from 0 infinity into 0 infinity measurable. Yeah? If this is true, then I can apply it to the particular case where x is a stable process. Okay? That is the other gap I left yesterday. Let me give you an intuition for this. So imagine the process starts at a position little x, okay? And then you wait until the first time the process goes below 0, okay? So it moves around. There are some jumps. And eventually it makes a jump. It goes below 0 and it continues moving. Okay? This is not the only possibility. Okay? Imagine you have a Brownian motion. A Brownian motion could go below 0, goes below 0 continuously. Okay? But there are other Lévy processes that have only jumps, but that they can still accumulate around 0. Okay? So we have two possibilities. We have the possibility when this is negative, but we also have the possibility of passing below 0 continuously. Okay? This is what is called the event of creeping. Okay? And it is worth knowing that x creeping downwards, okay, and it is worth knowing that x can creep downward even if there is if there are negative jumps. Okay? Because there may be a continuous part and the negative jumps that can force the process to accumulate. Okay? But that is why I have to take into account this event. Okay? I didn't do it yesterday because stable processes do not creep. Okay. Meaning that the probability of x tau 0 minus being equal to 0 is equal to 0 for every starting point. Okay? So that is why yesterday in the identity I gave you, I didn't put this indicator here. Okay? But okay, I will only take care of this one for my purposes today. Okay? So this time that is here, this tau 0 minus, okay? In fact, what it is the first time where you make a negative jump, okay, that is large enough. What do I mean by large enough? That I need to jump of a size that is bigger, okay, than this size that is red, okay? Which is this size that is here? It's just xt minus, okay? So if this happens at time little t, okay, that jump happens at time little t, the jump is necessarily bigger than this position here, okay? Instantaneously, this jump happens at rate pi of minus infinity minus x, where x is equal to xt minus. Okay? But I need, of course, that xt minus be positive, and I need more. I need that the whole path is positive. Okay? So I still need that t is smaller than tau 0 minus. Okay? But there is just one jump that does that. Before this one, there is no other jump that does this. Okay? And once I go below, okay, this condition is not satisfied. Okay? So there is just one jump that does that. Okay. How do I get that expression? So this is f tau 0 minus, yeah, indicator x tau 0 minus is strictly smaller than 0. So this is equal to the expected value starting from x of the sum when t is positive of f t indicator the infimum of xs for s strictly smaller than t is bigger than 0. Okay, so I haven't go below 0 at that time t. And there is a jump. So delta xt is different from 0. And that jump leads me from the position xt minus below 0. Okay? Delta xt, I should say that, delta xt is the usual notation for xt minus xt minus. Okay? So this sum, although it's infinite, okay, it's not a problem because this indicator is equal to 0 for all t, both for this one. Okay? Well, now that I have that expression, and I remember the compensation formula again, then I get that this is equal to the expected value starting from x for the integral between 0 and infinity of dt f t, the integral pi dy from minus infinity to 0 of indicator infimum of xs for s smaller than t is bigger than 0, and then xt minus plus y is smaller than 0. Yeah? Okay. But this is just another way to say that tau 0 minus is bigger than t. Okay? So this expected value is the integral from 0 to tau 0 minus dt ft. So the indicator goes out to here, okay? And I'm just left with this indicator here, okay? Which means that y should be smaller than minus xt, okay? So it's integrating the tail of pi. So it's pi of minus infinity minus xt, okay? And then by Fubini's theorem, this is equal to what I claim. Yeah? Okay. So in particular, this is a density for tau 0 minus on the event of non-creeping. Okay, so the event where x tau 0 minus is smaller than 0. Okay. So it is worth noticing that if there is a density for this random variable, for tau 0, okay, it will come from two parts that are disjoint. One that is the event of creeping, or the event of non-creeping, and the event of creeping. Okay? Okay. So that fills the two gaps I left yesterday. Are there any questions with respect to this? In fact, these kind of formulas are true for more general processes, and is a version of the Ikeda-Watanabe formula. That's just something that is good to know. Okay, so I'm done for this part. Okay, and then with identification, that is not a problem. Okay. So we saw that if y is the positive self-similar Markov process obtained by killing a stable process on minus infinity 0, okay, then y can be seen as the Lamperti transform of a Lévy process psi star, and psi star has a Laplace exponent psi of phi star, which can be represented by the formula which is a quotient of the gammas. gamma alpha rho minus I lambda gamma minus I lambda times gamma 1 plus alpha rho bar plus I lambda and gamma 1 plus I lambda. Okay. This holds for all lambda in R. And then we saw that the stable process obtained by conditioning to stay positive is absolutely continuous with respect to this one. Okay? And that absolute continuity relation is translated into an absolute continuity relation for the Lévy process that is behind. Okay? So we saw yesterday that the law of the Lévy process obtained. So I claim that Y oparu, which is the stable process condition to stay positive, is a positive self-similar Markov process, okay, and that you can check it using the density. Okay, once you see the density of the two processes, you can easily check that the scaling property is not perturbed by that. You can also check it with the limit definition. Okay, and then we have by Lamperti representation that this is the Lamperti transform of a Lévy process psi star. Okay, and then if we take P oparu, the law of that Lévy process, okay, then P oparu on Ft, okay, so the filtration of this process is equal to exponential to the alpha rho bar psi t p on Ft, where P is the law of psi, psi star, P star, P star. This means that the probability of any event with respect to this process can be determined with the probability of this process with this density. In the event that the process is alive. Okay. In particular, we can determine the characteristic exponent. Okay. So the expected value, just one bar, of exponential I lambda psi t. Okay. Okay, I'm removing the oparu here because I put it here. I avoid using, you notice already that, I avoid using too many times the hats. Okay. So this is equal to the expected value of exponential I lambda psi t. This is something that is Ft measurable, okay? And then I have alpha rho bar psi t indicator t is finite, okay? Yes. So this is the expected value of exponential I lambda minus I alpha rho psi t, indicator t is finite, okay, and by an argument of an analytic extension, this is just minus psi star of lambda minus I alpha rho bar, and then T. Okay. So yes, and on this side, this by definition is the expected value of minus T psi opar rho of lambda. And this holds for all lambda in R. So psi opar rho of lambda is equal to psi star psi star of lambda minus I alpha rho bar for all lambda in R. Okay, so by doing that I determine the other Laplace exponent. So if we do that, then we check that psi of lambda is equal to gamma alpha rho This is wrong. Sorry for that. I actually copied this one. Okay. Let me do that. So this one is the correct. Okay. And I will write the correct for psi star. Okay. Just psi alpha minus I lambda gamma alpha rho bar minus I lambda gamma 1 plus I lambda gamma 1 minus alpha rho bar plus I lambda. Okay. So this is the correct for this guy. That is what we should read here. Okay. But I actually copied the wrong one. So yeah. Okay. So just plug this value here on this expression here, okay, and you will get this one here. Yeah. Okay. We can do the same for the process condition to hit zero continuously, okay? Again, that is a transformation that will preserve the scaling property and the Markov property, okay? So the process will still be the Lamperti transform of some Lévy process, okay? That's what I said yesterday. And there is also an absolute continuity for that guy. There was just a minus appearing somewhere. I wrote that yesterday, okay? So, and I can do the whole thing for that guy. So if I take psi down arrow, the Lévy process associated to y down arrow, which is the stable condition to hit 0 continuously, we have that its Laplace exponent is characteristic exponent has the form psi down arrow, which is equal to gamma alpha rho plus 1 minus I lambda over gamma 1 minus I lambda gamma alpha rho hat plus I lambda over gamma I lambda for lambda in R. Okay. And if you see, all these three processes, okay, share that are the product of quotients of gamma functions. Okay, and that was something that was observed by Alexei Kuznetsov, and that motivated the introduction of hypergeometric stable processes, hypergeometric Lévy processes. Okay. Hypergeometric Lévy processes. So we have that for a beta smaller than 1, gamma in 0, 1, and beta hat positive, and gamma hat in 0, 1, the function psi theta defined by gamma 1 minus beta plus gamma minus I theta over gamma of 1 minus beta minus I theta times gamma of beta hat plus gamma hat plus I theta over gamma beta hat plus I theta, okay, for theta in R, okay, is the Laplace exponent or the characteristic exponent of an hypergeometric Lévy process, okay, and this product is conveniently written in such a form that we have a Wiener-Hoff factorization. Have that the function that theta is mapped into the quotient gamma 1 minus beta minus plus gamma minus I theta over gamma 1 minus beta minus I theta is equal to a function kappa of minus I theta, okay, where kappa is the Laplace exponent of the upward Laplace upward ladder height process. Associated to psi tilde. Okay. Psi tilde. And we can do the same, so we can do that theta map into gamma of beta hat plus gamma hat plus I theta over gamma of beta hat plus I theta is equal to kappa hat of I theta, okay, where kappa hat is the Laplace exponent of the downward ladder height subordinator of psi tilde. Who are those processes? Who are the upward and downward ladder height processes? So imagine you have the path of a Lévy process psi tilde. Okay. And then you keep track of the supremum. Okay. So the supremum remains constant when we are below the supremum, okay? Then it grows when we reach new supremums. And we do the same for the infimum. Okay? In fact, this path in blue, in red, sorry, if we delete these flat spaces, okay, we get a process H, okay, and H is a subordinator with the same image as St, which is given by the supremum of psi tilde S for S is more or equal than T, for T positive, okay? And then, if we keep track again of the infimum and we delete these flat spaces, okay, we get, and we take the negative, we take minus h hat, okay? And h hat is again a subordinator with the same image as minus it, which is minus the infimum of psi tilde s for s smaller or equal than t for t positive. Okay? These two subordinators are what is called the upward and downward ladder height processes. Okay? How do we delete these parts? Is by observing the supremum in what is called the local time scale, okay, of the supremum. And in the fluctuation theory of Lévy processes, one of the key objects to study is h and h hat, and what is left inside the excursions. So if we want to understand a Lévy process, a real valued Lévy process, one thing we can do is to study the supremum and the excursions. Okay? That gives us the whole description of the process, and an equivalent description can be obtained by taking the infimum and the excursions from the infimum. Okay? So the objects we have like this. This is an excursion from the infimum. Yeah? Okay, so we can do both things. They are dual, essentially. Okay? And it depends on the process we are studying, what is more convenient, or the kind of property we want to study, what we should choose. Okay. Are there any questions about this? So, where did I write that? This is by Kuznetsov. Okay. There are a couple of papers, at least, on hypergeometric Lévy processes and its generalizations. Okay? And this is dating from 5 years ago, around, and that was a big improvement in the theory of Lévy process, at least in the fluctuation theory, because there were not many examples of Lévy processes for which this factorization was known explicitly. Okay? And something I didn't say here is that the Lévy measure is known explicitly in terms of hypergeometric functions. That is why it gets the name of hypergeometric Lévy processes. Okay? So in terms of hypergeometric functions. Okay? Are there any questions about this? Kasu, you happy with that? Do you have any questions?
No, I was just reading I couldn't read the blue one, ladder height, what?
Ladder height subordinator of psi. Yeah, ladder height process, ladder height subordinator, yeah. Okay, so all these are particular cases of that formula. There are many other examples of this. There are other examples of hypergeometric processes related to stable processes via Lamperti transform as, for instance, if we take the norm, so if we take x to be a symmetric Lévy process, a stable process, and if you take y to be the absolute value of x, this again, because of the symmetry or the norm of x, because of the symmetry, this process is positive and Markovian, okay? So it can be seen again as the Lamperti transform of some psi, let's say tilde, double tilde, because we already use it, okay? And psi double tilde is again a hypergeometric Lévy process, okay? Psi double tilde is hypergeometric. Okay. There is another example. Maybe you have again X a stable process. In R. Okay. And then you draw the path. I should delete some bits because of the jumps. Okay. And then we remove every negative part. Okay? So we get rid of all this. Okay, and we glue together this path. Okay? So remove okay? How do we do that? I will tell you now. We take y to be x time changed by ct, where ct is equal to the inverse of the functional that grows only when x is positive. Okay, so we take a functional that grows only when x is positive. So the functional should look like growing, then stays flat because we are negative, and then it grows, and then it stays flat again, and then it grows, stay flat, grows, stay flat. Okay? So take the inverse of this functional. What is going to happen with the flat parts when you take the inverse of that? When you make this generalized inversion. The inverse will look like something that grows, and then it makes a big jump. Okay? And then it grows again, and then it makes another jump, and it grows a big jump, and so on. Okay? So this is CT. Yeah? C has a lot of jumps. And these jumps, they correspond to this size. Okay? So I will move from this position into this position. And then I keep this part because it's still there. I don't change the rate. The slope is 1 here, not in my drawing. But then I remove this bit, I jump to this bit, and so on. Okay? So the new process that is there the process obtained by deleting this the negative part is something that looks like there are a couple of this, and then remember I make a jump to go negative, okay, because x is a stable process, so it jumps below 0, okay, and then I remove whatever is negative, and then I jump again to become positive. Okay, so I glue this part of the process again. Okay, so I glue it where it makes a jump, then it jumps below again, then I wait until it becomes positive again with a different jump, so let's say here. Okay, so I add another jump, and so on. Okay, so what is your guess for the Lévy process that is associated to this one? So Y is also a positive self-similar Markov process. This is an exercise. It's not difficult. I really invite you to do it. We know it's Markovian because it's the time change of a strong Markov process. So Volkonsky theorem will tell us it is a Markov process, but it has the scaling property. So I invite you to check that it is a scaling process. It has the scaling property, and you can do it just as we did it at the beginning of the course. Okay, but Y is the Lamperti transform of some process psi prime. What is your guess for psi prime? What do you expect? What would you expect in psi prime? Do you think this is somehow related to psi star? Psi star, remember, is the process that describes the positive parts of the process. And here we're just observing positive parts of the process. And the positive parts of the process, they are all of them determined by the jump measure, isn't it? Okay. This new process, the process psi prime, also is only discontinuous, okay? Because this process is all discontinuous. It's a stable process, just time change. Here we are adding some discontinuities. That's important, okay? But so the Lévy is totally discontinuous, so this guy should also be discontinuous, okay? What would you expect for the Lévy measure of this guy? Any guess? Say whatever you think. Well, here, when you're positive, you have the same jumps. So the Lévy measure should be exactly the same. But from time to time, we add some jumps, isn't it? So we wait some time that is long enough to observe a new jump. Okay? In fact, what I just did is to add this jump, or this one. Okay? But look, these jumps are happening after a very long time. Okay? But in between these times, I leave the same jumps of the original process. So the Lévy measure of this guy is in fact the Lévy measure of this plus a jump plus a distribution, because I just have some jumps every exponential time. Okay, these are jumps that happen of some type, okay, of some particular type, and the jumps of some particular time that happen after a long period of time should be described by a distribution function. Okay, so the Lévy measure of the process psi prime is in fact equal to pi of psi star plus a distribution function psi f, yeah, and f describes the blue jumps. In fact, this, what it's telling us is that psi prime is equal to psi plus a compound Poisson process. So let's call it plus C, where C is a compound Poisson process with rate C minus divided by alpha and jump distribution F. Okay, I'm not giving the explicit formula of F. But why do you think there is a C minus divided by alpha? Remember, C minus divided by alpha was the rate at which we killed the path of psi star. Okay? Because this length that we have here follows an exponential distribution of parameter C minus divided by alpha. Remember, the Lévy process that describes the negative part, the positive part, sorry, is killed at an exponential time of that rate C minus. Okay, so the length of the path that we observe here is exponential of that parameter. Yeah? Okay. So this is the rate at which the jumps of this compound Poisson process appear. Okay? And then the distribution F was determined by Cipriano, Pardo, and Watson. Okay. I'm not sure. I think it was something related to beta functions. Okay. Are there any questions about that? No? Okay.
For the case that X is a right
Yeah, when it is a Brownian motion, then we just take reflected Brownian motion, okay, and that is not covered by this guy. I agree. Yeah. Yeah. So x is always smaller than 2. Alpha is smaller than 2. Yeah. That's a different description, because that process will zero will be recurrent and regular and recurrent, and that's a different story. Okay. Remember that the Lamperti transform of a process never hits 0. Okay, or if it does it dies. Yeah. Okay. And that actually, your question takes me to the next topic, which is the topic of entrance laws. Of positive self-similar Markov processes. Okay. So observe that if we take x that is a positive self-similar Markov process that is obtained as a Lamperti transform of some Lévy process I, okay, so x will die at 0. Okay. So Lamperti in his paper of 1972 asked the question whether we can include 0 in the state space of x. Okay. By asking that, I'm just asking that the process will not die at 0. Okay. So that x does not die at 0. Okay. So we should be able to start x at 0, okay, and if x returns to 0, then 0 is a recurrent state. Okay, because of the Markov property, if we return once, we should return infinitely many times, and it is regular. And regular because if I visit 0, I should return to 0 immediately, and that is a consequence of the self-similarity. Okay, so the return times should cumulate in some places until eventually it goes below 0, beyond 0. Imagine what happens for a Brownian motion. Brownian motion reflected. Okay, so if we take absolute value of Bt, that is a process that if it starts from x, it moves, it hits 0, and then it returns to 0 many times until eventually it escapes, and so on. Yeah? Okay. So by these kind of accumulations at 0, we mean regularity. Okay? And if we take Y to be a Bessel process of dimension 3, okay, we know that this process is a positive self-similar Markov process. We saw that in the first day, okay? And that process, in fact, can be started from 0, but it never comes back to 0. Okay? So Lamperti asked for which processes we can do this. We can either start from 0 and maybe never coming back, like for the Bessel process, or if we come back, then we should come back in such a way that 0 is a regular and recurrent state, like Brownian motion reflected. Okay? The first question was answered by Bertrand and his co-authors. So when can X, that is the Lamperti transform of some Lévy process, can be started from 0 and X does not return to 0. Okay, so T0 is still infinite. Okay, and one way to do that is to start the process at some point, leave it free, okay, and then make X go to 0 from the right. Okay, and the question is whether there exists a probability measure P0 plus that can be obtained as the limit as X goes to 0 from the right, weakly, in the Skorokhov sense. Okay? If we can do that, then we can start the process from 0, and it will never come back to 0. Okay? That is what is happening for the Bessel process. So the question is whether we can do that, and the answer was obtained by many people. So it was Bertrand and Caballero, and then Bertrand and Jor, and then Caballero and Chaumont, and then Chaumont, Cipriano, myself, and Pardon, I think. Yeah, Pardon Rivero. Yeah. Okay. In a series of papers, we prove that P0 exists and it is non-degenerate. Okay. If we have, for instance, that psi1 is finite, has a finite mean, and the mean is strictly positive, okay, and or the expected value of psi1 is equal to 0, and the upward ladder height process of psi has a finite mean. Okay. In fact, these are all the cases in which the upward ladder height process has a finite mean. Okay? But this is just telling us, okay, that the process psi should go to plus infinity. Okay? Fast enough. Okay. And the reason for that is because if we want to make the starting point go to 0, remember this is the exponential of psi. Okay? So from here to the right, okay, we have a path of psi. We have a copy of psi. If you observe at any time t, to the right, the path of x from that time onwards is just a copy of the exponential of psi. Okay? So, to make this part of the path to move to 0, okay, I need another process, psi prime, okay, which should also be of infinite length. Why? I should be observing an infinite length of the path, because I need this path to cumulate at 0. Yes? Okay, so this will become the lifetime of the process psi prime. Okay? So I need two processes. Okay? One it is driving this part of the trajectory, and this one that is driving the left part of the trajectory. Okay? But I need also that this process escapes fast enough so that it can go to plus infinity, because it's going to minus infinity on the left-hand side. So I need this process to escape from minus infinity. Okay? So I need this kind of a condition to ensure that the process can escape from minus infinity. Okay? So the path that will describe this process so P0 plus is construct building a process psi star, okay, on minus infinity, okay. So here we have minus infinity, here we have plus infinity, and it should be coming from, this is not a good, yeah. It should be coming from minus infinity, and then go to plus infinity. On the right hand side, because on the right hand side I observe just a path of x, this should look like psi, okay, on the right. Okay, here I should observe something that looks like psi. If I go in this direction, I'm observing actually something that looks like psi, but run backwards. Okay, so here I should have another process, psi, but this process is going to minus infinity, isn't it? So I need to force that process to go to minus infinity. Okay, so in fact, this guy that is here is the dual of this guy, forced to go to minus infinity. Okay, so the guy that is here is the Lévy process conditioned to go to minus infinity. Okay, the dual Lévy process conditioned to go to minus infinity. Okay, and this construction was made explicit by Bertrand and Savov. Okay, but there are other constructions in these papers. Okay, and I in purpose wrote this because this overshoot, this jump from 0, we can observe it in many places. Okay, and that overshoot that is here is coming from the way we pass above levels, and we stick this new process, okay? And that overshoot should be stationary, okay? And the stationarity of the overshoot is guaranteed by this condition. I don't say more, okay? But these overshoots should be stationary. Okay? Okay, are there any questions? Let's make a break for the moment and then we continue.